I will begin. So, hello everyone. My name is Lizette Wong, and I'm an undergraduate student at the University of Texas at Austin. And I am joined by my co-author in the audience, who is Zoelle Wong, and she is a PhD student at Georgia Tech. And today at this talk, we'll be discussing the audio performance comparison analysis of biocomposite bassoon reed design. So in this talk, we'll be examining three audios from three different types of reeds, and we brought them here today to listen to. So let's see if you can hear the difference between these three recordings. So here's the first one on the cane reed playing an F2. This is a Leger reed, which is made of polymer, also playing the same note. And this is a fermato reed, which is a biocomposite reed. So for me, I thought these were all pretty similar, and the key to understanding the differences between these audios is to understand the mechanisms behind the reeds, and more importantly, what a reed is. So for those of you who don't know, bassoon reeds are the mouthpiece of the instrument, and they attach to the bocal of the bassoon. And they come with their own shortcomings in that they are expensive to purchase from either a factory-made one or from people who make them. They're time-consuming to make by hand, and they are quite short-lived. On average, they live around 1 to 3 months before they expire, and the process repeats. So as a result, bassoons are searching for newer options or reeds made of different materials that could possibly last longer. And this recurring cost often causes people to leave the instrument or quit bassoon very early on because they cannot upkeep with the cost of reeds. So overall, we hope to increase accessibility by removing the economic barriers to learning the bassoon, and we are developing a biocomposite bassoon reed that is more cost-effective and durable. But we do want to know how it compares to its competitors. So the goal of this talk is to compare and analyze the audio performance of biocomposite, polymer, and cane bassoon reeds. So for some background information, currently available on the market, there are two types of reeds. The first is a traditional reed made from cane, as you see here, which can be bought ready-made from music stores or made by people's lesson teachers from scratch. And the second is polymer reeds, which are synthetic reeds, and the common makers are Silverstein, carbon fiber reeds, and Leger reeds. Now, Zoe and I have developed a brand new type of reed, which is a fermato reed, a biocomposite, made from cane and resin in a two-step chemical process. The first step is deliquification, which removes the compounds of lignin and cellulose. And the second step is backfilling, which replaces this with the resin and reinforces the remaining structure. This process is brand new and it has not been done in literature or patented before. So not only is this an acoustical study, this is also a chemical study as well. And as a result, we're using a chemical process to alter the material of the reed itself, and we did this in the Lynn Lab at UT Austin. So for previous works, there is limited research on double reeds in both the musical and scientific communities, with indicating a greater gap in literature for comparing synthetic and biocomposite reeds. So within the bassoon community, we conducted 60 open-ended interviews with student and professional bassoonists, and we asked them the following questions. 1, what do you not want to change about your reed source? 2, why do you not currently play on synthetic reeds? And 3, who bought your synthetic reeds? How many did you buy? And how long did they last? And overall, we received mixed claims on sound quality between synthetic and cane reeds. There is not really a consensus in the bassoon community about these. Within acoustical science, we did find a paper published by Gonzalez and Prati, which proposed FFT-informed dimensionless descriptors for wood-cade reeds, followed by principal component analysis in a subsequent paper. And this was published in April 2022, and you can read more about it here. And we'll go into this study more later because we will do some cross-analysis. So for our experimental setup, we recorded 3 notes, which were F2, F3, and F4, which span the 3-octave range of bassoon. And we took the bassoon analog signal, we sampled it at 44.1 kilohertz. We routed it to an AKG C414 condenser microphone, then to a Scarlett interface, to a laptop using Audacity recording software. And then every note was played 5 times to average the reed's behavior. And this is a brief screenshot from Audacity with the envelope and the attack the decay, and this is the spectra of the reed. And this is what our experimental setup looked like. So we set up the audio rig in the anechoic chamber at UT to minimize noise, and we took the bassoon boot, which is the bottom aperture, and placed it 78 inches away from the microphone to prevent some near-field effects. And then from here, the block diagram, you can see the microphone, the interface, and the laptop, and our friendly bassoonist here. So after we took the recordings, we began to post-process the data, and we first did this by finding the single-sided FFT for all 5 samples. And this is exemplified by this plot, which is F2 on a cane reed. And after that, we normalized it to the frequency response of the microphone, which was recording white noise, and we converted it to decibels using the reference pressure of 20 micropascals for air, and then we took its average. And then from there, we could derive these 2 images. This is the averaged spectrogram, and this is the normalized single-sided FFT, which was done with a moving average window using a Hamming window at a 50% overlay. And then we found the timbre coefficients, and we cross-compared them with the Gonzalez paper. We also, I'm not sure why this is here, but we also find the small standard error. And we did this by taking the standard deviation divided by the square root of the size of the data population, averaged it by 5, and we did this 9 times for the 3 notes on the 3 reeds. We found that it was less than 0.2 decibels, which is very good correlation considering we had a human tester. And as we know, humans are quite variable when using them in experiments. So these images are the averaged power spectrograms for all 3 notes, F2, F3, F4, and all 3 reeds, cane, Leger, and Fermata. And we did this for the first 1 to 2 seconds as a function of frequency and time. And this color bar is the graph, kind of small, but it's right here. And what we found is that the spectrograms of the Leger and the cane show similar behavior, and this actually contrasts with our human surveys, which people thought they felt and sound different. However, the Fermata reed has higher vibrations at higher frequencies for all F2, F3, and F4, and this is evidenced by the bright colored striations across all 3 spectrograms, so higher noise overall for the bio-composite reed. However, our human tester, who is a professional bassoonist, did not perceive an audible difference. So although he said the reed felt different in his mouth, he couldn't really hear a strong difference. So after that, we found the normalized average single-sided FFT for all 3 notes on all 3 reeds, and we did this by taking the averaged FFT and dividing it by the maximum of the average to get these nice lined up at 1, and so you can visibly see the differences between the 3 notes. So we did this for F2, F3, and F4. And this top image, we overlaid or superimposed the F2, F3, and F4 for the cane, Leger, and Fermata reeds. And as we can see, the natural frequency occurs around 10 squared, which are these peaks. And then past that, we see a lot of this, which is the higher harmonics, which they look to be roughly monotonically decreasing, and they stop around past 10 to the 4th power. And these results indicate a bassoon reed contains non-negligible higher harmonics at higher frequency, and this appears for all 3 reeds. And we believe this is because the bassoon reed is a double reed, so fully coupled fluid structure interactions exist between the upper and the lower blades. And you can actually read more about that in this paper, which was published in March 2021 by Yoshinaga. After that, we found the normalized average relative to the cane reed. So we did this by taking the normalized Fermata and Leger FFTs and dividing it by the cane, because at the end of the day, no matter if it's a plastic or a biocomposite reed, we want to know how close it is to the real thing. Cane is the standard which we want to compare everything to. And what we found is that there is less than a 15% deviation at higher frequencies, or F greater than or equal to 1 kilohertz, for all 3 graphs. And then zooming in quite a bit to look at the natural frequencies, what we found is that it's approximately 1-to-1 for both reeds, namely Leger and Fermata, with the Fermata reed having a higher deviation at F2 and F3. Now, F4 looks a little bit different than F2 and F3. There's a sharp gradient, and this could be explained due to difficulty sustaining the pitch. You can think about this as if you were a baritone singer trying to hit a very high soprano note. your tone could probably waver a lot, and you could have a bunch of peaks and valleys. And so that explains why this graph has a lot more bumps and ridges compared to the smoothness of the F2 and the F3 graphs. So lastly, we found the timbral coefficients, and we cross-compared them to Gonzalez's paper. And what we found is the frequency centroid, which is the weighted average of frequency. And we did this by multiplying the amplitude and the frequencies divided by the sum of all amplitudes to calculate the centroid. And we also found the affinity, which is the relative intensity between the centroid and maximum principal frequency, or the frequency of interest. And there are no real analogous Western musical equivalents of centroid or affinity. However, these are very useful metrics for comparing them, or the notes, to each other. And so what we found is that our recordings had good clustering, they were close together, but they deviated quite a bit from Gonzalez's paper. And one possible explanation for this is the different recording environments. We were in an anechoic chamber, whereas Gonzalez was using a database, and they recorded their data in a recording studio. So this could possibly suggest that timbral coefficients do change and are dependent on your recording environment. So in conclusion, F2, F3, and F4 were played for the Kane, Leger, and Fermata reeds. And we did an audio performance analysis informed by average spectrogram, the normalized average single-sided FFT, and the timbral coefficients. The spectrogram results indicate that the Fermata reed contains more noise, and the normalized average single-sided FFT indicate that the Leger and Fermata reeds performed as well as Kane at their natural frequencies. Lastly, the timbral coefficients deviate from Gonzalez, but in comparison to Kane and each other, the reeds show similar behavior, which is a good sign. So for future work, we would like to do more material and post-processing analysis to investigate the cause of noise in the Fermata reed. For material analysis, we're thinking of using SEM, which is scanning electron microscopy. And for post-processing, after the reed has been constructed, bassonists will often whittle, sand, and fine-tune the reed. And we noticed that Hugh, the tester, said that he did a different post-processing method for the Kane reed versus the Fermata reed. So we think this might have an effect on the results. Secondly, we'd like to do a psychoacoustic analysis to understand the factors of sound perception. And we could do this by measuring more notes and melodies in a performance space and in a concert hall, and then giving them to surveying humans and seeing if they can hear the difference. And we'd like to acknowledge our sponsors, our mentors, our professors, and our teachers who've helped us along the way. And we are now open for questions. Thank you so much for listening.
Thank you so much. We have already some questions. The first question has been already replied in the meanwhile, because Gary was wondering and assuming this was played by a human. And already your co-author mentioned, yes, this is the case. And also Gary was wondering if you thought about durability issues.
For durability issues, are you referencing the Fermata reed? I'm assuming so.
The differences in between the reeds.
Oh, the differences between the reeds. We did like 3-point bending tests on the Fermata reed, and we did find that it was stronger. But different reed materials also affect reed beating. I'm not sure about that, but we can look into that later. I also think that another thing we could do to make this more robust is to take more samples amongst different types of reeds and different musicians, because every musician makes their reeds slightly differently. And that could impact the results as well. Yeah. There's also 2 schools of reading. Yeah. That could also affect things as well.
Yeah. So while we are setting for the next presentation, we still have time for some more questions. If you want, then we'll have Miranda. And there's one more question. So we suspect, no, this is an answer, okay? One of the main benefits of synthetic reeds is that they are more durable, right? Gary is asking.
Yes, they are more durable, but a downside is that they cannot be modified, and every bassoonist likes to tune the reed or shape it to their mouth. Some people like it longer, shorter, flatter, or not flatter, and a synthetic reed is kind of a fixed piece of plastic. You can't sand or file it to change its shape. So while they do last longer, a lot of bassoonists don't like it because they just have to play on what they have. Another issue why they don't like synthetic reeds as much is that they vary a lot. So I know we surveyed some people, and they would oftentimes buy 10 sets of reeds just to find the one they liked. I don't know. I hope that
see.
answered the question.
I think so, yes.
Okay.
Also, I'm sure you would need either more players or to find a way to do this a bit less subjectively. So to have some method, either
Yes.
a blowing machine, something that keeps you then not having the influence of the player in your results. Because yeah, at the very high frequencies you could see something, but this might also be out of chance. So yeah, maybe a bit more. If you have more players, this will be fine, or just try to have a way not to have the player at all. That would be an option.
Yeah, having like an artificial mouth, or I think taking more human testers would be better because everyone makes their reeds differently and plays the bassoon differently. So there's a lot of subjectivity here.
Sure. Yeah, we have also Jonas saying that he's able to reshape his. I assume that's a synthetic reed for the saxophone as well. So also plastic reeds could be modified, but I assume for bassoon might be different since it's two reeds. So there's space for research still here.
Yeah, there is a lot of space, and we only surveyed 60 people, so there might be people who do it differently as well.
Yeah. Also, your co-author is mentioning this, that since it's a single reed, a saxophone reed might be easier to modify. But yeah, that's a reason why the bassoon has been the last instrument to get the attention of the companies making synthetic reeds, because it's apparently not as easy as it has been for the other instruments. So yeah, we thank you very much for this
Thank you so
presentation.
much.
And we will slowly move to the next presentation. This will be by Miranda Jackson. Miranda is also